Hello, everybody. Welcome to this week's Green Bank Observatory Community Zoom. Just a couple of announcements before we turn it over to our speaker. You may have seen some stress in the government yesterday about funding and some confusion. So as I understand it, there was an OMB directive memo that was ordering a pause on all grant funded related activities. That pause is now been stayed by a federal judge, and that's where we are. So the observatory, as I understand it, still has access to its funds, and we'll just have to see how this all plays out. We will continue business as usual, and we will follow all federal directives. And right now, we just need some guidance and some clarification from the OMB and the NSF as to how to proceed. But we'll continue to do business as usual. One of those businesses as usual is our proposal deadline is today at 5 p.m. So if you haven't started your proposal, you have just enough time to write a compelling proposal and get it in by 5 p.m. today. I will be retiring, and my last day of work will be next Friday. And in the interim, Tony Remajon has graciously agreed to serve as acting Green Bank Observatory Director for the next several months. I think it's through September. So let me introduce Tony to you all. He should be familiar. He's a Green Bank user, has been at NRAO for many, many years, does a lot of his science using the Green Bank telescope, doing astrochemistry. So Tony, I'll turn it over to you if you want to say a few words.
Oh, just thanks, Jim, for everything you've done over for Green Bank over the last several years during your tenure. It's going to be big shoes to fill, but I think that we got a great team and a great organization in the process. So hopefully the transition will be seamless. And you've also put in a tremendous amount of process and procedure in place that will carry on here over the next several years after you left. So thanks for all the work that you did over the last several years. We're going to miss you, and hopefully you'll remain a GBT user for the years to come. Along with everyone else on this call, I hope to see everyone else that is on this call submit a GBT proposal by the end of the day today. If you haven't, or you're not, able to, please let me know, and we'll try to get you on the telescope. So with the science, the great science that the GBT does. So with that, I'm going to hand over to Dave, who will introduce our speaker, who I've also known for a pretty long time now. Very interested to see what he has to talk about today.
Yeah, thank you, Tony, and thank you, Jim. Our speaker today is Jack Gallimore, and he will be giving a presentation on the NRAO high sensitivity array, talking about magnetic fields and AGN accretion disks. So Jack, go ahead and set up, and I'd like to remind our participants, if you have questions, you put it in the Q&A box, and we'll take care of it after the presentation. So take it away, Jack. Thank you.
All right, thanks, David. And thanks for at least getting started on the title. I realized when I was making this slide that the title's a bit much, and so if I read the title, I'll only have time for questions. But the point of this talk is that we use the high sensitivity array, importantly, the VLBA, including the Green Bank telescope and the phase VLA, to take very sensitive measurements of polarization among 22 gigahertz water vapor megamasers and a fairly famous active galaxy, NGC 1068. I should back up a little bit and point out that the goal was not to get polarization. We had assumed that we would not detect it. Our real goal was to measure, to get a very high resolution and sensitive 22 gigahertz continuum map, which we did. We threw in the polarization because why not? But I think that turned out to be the most exciting thing. I would like to highlight the role of two students. One is Sam Agolpasand, who recently got her master's degree from Al-Zawra University, and she's applying for PhD programs now. And also Virginia Hostetter, who's about to graduate Bucknell University with a degree in physics. I tried to talk to her into astronomy, but she's going to pursue medical physics. So good luck for her. What I'll do is I'll kind of give you a broad overview of the geometry of NGC 1068. And then I'm going to take kind of a historical approach that leads to the detection of the polarization in the masers. So, oops, let me get out of this mode. All right. Right, so this is NGC 1068. On the left side, we have a fairly famous HST image reprocessed to look a little more glamorous. This is the inner few kiloparsecs. There are some fainter arms that extend farther out. And if we zoom in right here, and in fact, I should go back to my pen here. Right in here, let's try that again, is the region we're talking about. That's the narrow line region, that kind of burned out region in the center. If we zoom in on that famously, looking at it with the VLA, it has this, well, I wouldn't say it's a classical radio jet. It's about as good looking a radio jet as you find in a Seyfert galaxy. And just I should point out, NGC 1068 is famously one of the first Seyfert galaxies. It's one of the most famous Seyfert 2 galaxies. And of course, the thing that makes it probably most famous is it's known to harbor a hidden broadline region, implying that the black hole, the accretion region, is surrounded by some dusty medium that's obscuring our direct view. Now, if I go over to the radium map, and again, this is actually produced by a PhD student, Isaac Mutu, I think just finished. I think he just received his PhD. We're going to zoom in right in this region, the so-called radio source S1 region. It's a flat spectrum radio source, which is identified with the AGN, and it's also associated with a water megamaser disk. Not entirely dissimilar to the more famous one in NGC 4258, but also a bit messier, which has made it challenging to analyze. And I'll show you a little bit of that. Okay. So these are just zooming in. One of the things I want to highlight in this talk is that there is a massive outflow from the AGN region. So on the left side, this is actually an infrared image taken with the Symphony spectrograph. It shows a Merlin continuum image in green. This is one of my images from like 20 years ago. Again, the nucleus is right here, this S1 region right here. And what we're seeing is an emission line image of iron 2 in the infrared H band. And I think this best shows the overall outflow. It has that sort of classic hourglass shape. You might think this was a planetary nebula if you didn't know more about it, for example. There is a molecular outflow associated with that, but it's a little bit harder to see on integrated flux images just because there's so much molecular gas in this region that it's hard to distinguish the rotating Galaxian disk from the outflow from the AGN. On the right side here, we see a zoom in even closer, right? So we're zooming on S1. We're getting down to the few parsec scale. The sort of color scale is an ALMA image. At the time, it was the highest resolution image of HCN 3:2. And these are the first sort of images of this dusty molecular gas that's hiding the central engine, right? There's some kind of disky-like thing that's surrounding this, what we call the torus. And one of the big questions, actually for decades now, is how do you actually have a molecular disk orbiting a black hole and give it sufficient scale height such that you wind up hiding the central engine in the appropriate number of hidden AGNs? And the idea is that you have to have a scale height that's kind of comparable to the radius. So that's not stable. So how does that scale height maintain? And deep inside there, I show, again, this is an ancient map now, probably almost 25 years old, of a VLBA image I took, the 5 gigahertz continuum, showing that weirdly, it's actually oriented perpendicular to the outflow axis. And so we've been interpreting it as a disk, an ionized gas disk, a hot ionized gas disk, rather than a more traditional VLBI interpretation, which would be a jet or something like that. All right, so now we're going to zoom in way down here. This is where the masers are. They basically occupy the region surrounding this VLBA continuum source. Right, here we go. And so again, looking at historically, this was for the longest time the VLBA image of the maser disk of NGC 1068. So on the left side, you're seeing this is Lincoln Greenhill's work back. I think the observations were 1996, and they appeared in a conference proceedings in 1997. What you're seeing is a map, a sky map, right, north, south, east, west, of water maser spots. So spots are defined as basically photocenters on individual channel maps within the spectral line cube. They're gray scaled according to velocity. And so to the upper right here, right, to the northwest, these are red shifted masers. The darker ones are blue shifted over here to the southeast. And overall, it kind of gives a rotation pattern, just like NGC 4258 and other water megamaser accretion disks. Again, the scale now, we're getting down to, I believe the diameter across here is something like 1.5, 2 parsecs from one extreme to the opposite extreme. And I highlight the local jet axis that we measure using the Merlin image. Okay. One of the things that came up that was peculiar about 1068 compared to other megamaser disks is revealed when you make a position velocity diagram, right? So you do the usual thing and measure offsets along the disk axis, the major axis, and plot velocity versus radius. And you see what you'd expect. Again, 4258 has a very similar sort of plot where you see a straight line, right, from one side of the black hole to the other. And that straight line indicates that you're looking at masers at a common radius. And the conspiracy of geometry is, and the Doppler effect, is that you expect a straight line if they're all at the same radius. Okay, there's a little scatter here, but it looks like what you expect. Then when you're looking at masers beyond that inner radius, you start to sample the rotation curve. And it's thought that these masers are preferentially amplified along the kinematic line of nodes. So if that holds up, you're literally sampling the rotation curve, which should be Keplerian. And the weird thing is that it wasn't Keplerian. It just a sort of naive interpretation of the PV diagram indicated that the fall off was slower than Keplerian, which led a few authors to suggest that, well, maybe the disk itself is self-gravitating. It's a very massive disk. And it's a little bit embarrassing almost that the mass of the disk has to be almost as massive as the black hole, which the total mass is around 16 or 17 million solar masses. And it's hard to imagine how exactly that's stable. But again, it also depends on a lot of assumptions about the PV diagram, which don't necessarily hold up. And Violetta and Pellizzeri and I have done some follow-up analyses that show that actually it could be Keplerian fall off if you consider the full 3D spatial distribution of maser spots. Okay, so we were motivated, Violetta and I in particular were motivated to go back and revisit this. We were particularly curious about this flat rotation curve. And we're also curious about just going back with now the high sensitivity array. This wasn't really available back in 1997. There was, or at least the GBT was not commissioned yet, certainly. And with the HSA, right, you have the VLBA plus now two very sensitive antennas, the phase VLA as well as the GBT. Which fundamentally helps with calibration. That's the most challenging thing with these data sets. But also, there's also the major upgrade where we now have intermediate frequency channels that are much broader. So for example, looking at this left plot again of the maser spots, to span the velocity range, I believe it was plus or minus 350 kilometers per second or something like that relative to systemic. I think Lincoln had to use 7 or 8 intermediate frequency bands, just narrower bands at the time, to cover the full velocity range. And now with the wider intermediate frequency channels, we can get them all in one IF, which makes calibration and analysis a lot easier. In fact, I can admit I tried my hand at reducing these data, and it was really a challenge. And I assumed at that point I would just give up and try the HSA instead, and I'm glad I did. So let me show you the results of that first observation. Let me see. Here we go. Let me clean up some of these annotations. Right. And so here again on the left side, I'm showing now our spot map of the water masers. So this is now the high sensitivity array, VLBA, GBT, and phased Y. We chose not to add European telescopes because, you know, the peak maser flux density is around 200 or 300 millijansky, and they're starting to resolve out already on, say, baselines between, say, the VLA and St. Croix. And so, you know, maybe we could have gotten them with Effelsberg, but it was diminishing returns at that point. So there's a spot map. I plotted it on top of that 5 gigahertz continuum image. The beams are shown in the lower right. The larger blue beam is the 5 gigahertz beam. The small white beam is the 22 gigahertz beam, the water maser beam. Right, and you can see roughly the same pattern that Lincoln had observed. We discovered a new maser group, which is what we call the B1 group right here. You see the general pattern of red shifted to the northwest and blue shifted to southeast. But the thing that stood out, and in fact, I really should go back to the previous slide and show Lincoln's map again. Let me see if I can do this. Hang on. You'll notice looking at Lincoln's map here that there are these kind of weird kind of linear structures within the map. And Lincoln had pointed that out. And again, this is a conference things he didn't really go far other than say, aren't these interesting? If we go forward, let me go back to this, to our map. If you zoom in specifically, say on this R4 region, that's shown over here on the right side. So again, this is just a spot map. The colors here are not velocity anymore. They're just identified groups that we use the clustering algorithm just to identify separate groups by space and velocity. And you see all these beautiful stripes. And we were immediately drawn to the conclusion that we're looking at something that kind of resembled filaments that you would see, say, in solar prominences, right? These look like magnetically ordered structures. And we did some calculations about, what kind of magnetic fields you would need to stabilize these structures. And it turns out as long as the fields are greater than a few milligauss, you're stable against things like turbulence and differential rotation, sort of locally over these filaments. Okay, so that's our setup. Now, one other thing we got from this observation is that we did get a detection of continuum on short baselines. And so we produced a tapered image for of the line-free channels. So again, we only observed this with one intermediate frequency channel. And so we used the N channels that were line-free to make a tapered continuum image. And that's shown here on the right side, right? So here again, the dots are the maser spots. And the contours are, basically the weak continuum that we're able to get on the shortest baselines. The beam for the tapered continuum is given to the lower right here as the blue ellipse. The other thing we discovered is that when you look at the PV diagram, this straight line that we would expect for masers that are at a common radius wasn't really a straight line. So we benefited from higher sensitivity, just detecting way more spots. So we're able to see the line in detail, and it's really more of a curve rather than a line. And we tried several models. The one that worked the best is that we think we're looking at a spiral arm within that disk. So in other words, the masers aren't all at a common radius. Instead, you're sampling gas along a spiral arm that's nearly at a common radius, but is winding outwards, which introduces that curve in the PV diagram. Okay, so that catches us up to what the newest observations that I want to present. We said, wow, we're actually getting continuum. We never predicted that we'd see 22 gigahertz continuum. The surface brightness of the continuum is very low. 22 gigahertz is very challenging. And so we went back and observed a second epoch with again, the masers and one intermediate frequency band. And then we also added 3 pure continuum intermediate frequency bands to try to produce wide bands to get a sensitive continuum image. And rather than dwell on all that, I'll just show you what it looks like. And that's on the left side. So the contours are the new 22 gigahertz continuum image that we got as part of this new HSA observation. And of course, the colored dots are, as you would expect, the photocenters, right, the maser spots. A couple of things to point out. There has never been a compact, or prior to this, I should be careful, prior to this image, we've never detected a compact radio source in NGC 1068. It's always been resolved. They keep going to longer baselines, and it always resolves into this disk-like thing, or this thing that's sort of oriented like an edge-on disk. This is our first shot here. There is a compact source here. It's unresolved within the extended continuum structure. We're calling it NGC 1068 star, an analogous to Sagittarius A star and M87 star and so on. Presumably that's the location of the supermassive black hole. And sure enough, it sits right atop or behind, whatever the right word is, the systemic velocity masers, right? And so one of the things we draw immediately is that we are looking at something that is pretty edge on, that we're seeing the near systemic masers right on top of presumably the location of the black hole. We also have this nice detection of a little filament going to the north, or some radio extension to the north. That's this thing. We're calling it S1 North formally. We refer to it more affectionately as the foxtail. based on a colleague's comment when they first saw this image. So we're presuming that we're looking at some recent ejecta along the radio outflow axis, right? So the continuum image was very successful and it's very pretty. And we did do some, and now we have a better constraint on what the likely kinematic center of this maser disk is. And we have not done that modeling yet because over on the right side, we were more excited to actually detect something that had not been seen in extragalactic masers before, which is to say linear polarization, right? So what I'm showing you in this grid, each column is a separate Stokes parameter, or the last column is actually total linear polarization. Right, so you see Stokes I, total intensity in the first column, and these are the 5 brightest channels. You can see the detections in Stokes Q, mostly negatives. You see detections in Stokes U, mostly positives. And then, of course, we have the total linear polarized signal, which is going to be an absolute value, right, showing up these bright spots. One takeaway is that, look, we're really at the limit of signal to noise here. These things tend to be sort of in the, happily greater than 5 sigma, but not much greater than 5 sigma. And so we have some confidence in these detections. And there's a whole battery of tests we applied to assure ourselves that we believe in these detections. That if there are questions about them, I can talk about those later. So we have polarization, which again, we certainly weren't expecting. Let me show you what the maps look like. Right, so again, this is the same image on the left side, again, showing you the continuum. This time I have a scale bar, the 1 parsec, so you can kind of get a feel for how close we are to the central black hole. But if we zoom in on the R4 and R3 region, right, the R4 masers and the R3 masers, they're over on the right side here. And I've superimposed the EVPAs, right, the electric polarization vector orientations, right? And hopefully you can see right off the bat, you can see these filaments, right? Some of them are roughly parallel to the disk plane. Some of them are at a slight angle to the disk plane. But all these electric polarization vectors are perpendicular to these filaments, okay? So the fact that we see these kinds of common patterns of organized filaments and polarization that's perpendicular to these filaments, I think makes a pretty convincing case that we're seeing magnetically ordered structures. Oh, sorry, it occurs to me one thing I completely forgot to mention. I've been talking about water masers. Water ostensibly is a neutral molecule. Certainly that would be true for these masers. But these masers are thought to arise in partially ionized gas. These are X-ray dominated regions of the molecular disk. And so we're looking at partially ionized gas. And so magnetic fields, hopefully, it should play a role in organizing these structures. So one of the things I always tell my students not to do in giving a talk is show a table. So I'll show this table. And this is just a summary of all the properties of the H2O masers. The only thing I want to focus on is the last column. This is the angle between local filament axes and the polarization axis, right? So 90 degrees means it's perpendicular. 0 degrees would mean that it's parallel. And this is just a verification. You can read down the column, read down the numbers if you like. It's perpendicular, right? They're all consistent within 3 sigma of polarization vectors being perpendicular to filaments. None are consistent with being parallel. Okay. So where do we go with this? Well, it's hard to constrain the orientation of these magnetic fields. Normally what you would do is use a circular polarization as a measure of the line of sight component of the magnetic field, and the linear polarization to measure something about the sky plane orientation of the magnetic field, and use the ratio of circular to linear polarization to get an orientation of the magnetic field relative to the sky plane. There's no circular polarization detected. Water is a non-paramagnetic molecule, and the circular polarization is pretty weak when we're talking about milligauss fields, pretty much undetectable. However, there is this property in the linear polarization that you predict either parallel or perpendicular polarization relative to a magnetic field line, depending on the orientation of the magnetic field relative to the line of sight. And so basically, if the magnetic field is more or less pointing towards the observer to within 55 degrees, you expect parallel polarization. If it's opposite of that, or the complement of that, within 35 degrees of the sky plane, you expect perpendicular polarization, right? So the way we're interpreting this is these filaments are showing, it's just like in solar prominences, the projected orientation of the magnetic fields. And the fact that the polarization is perpendicular to that is telling us that we're likely looking at magnetic fields that are closer to the sky plane, although we can't measure more precisely than within 35 degrees, right? And so that gives us a sense of how the magnetic field is oriented with respect to the disk itself. And that takes me to my conclusions here. This is going to need some modeling, right? So we're at the speculation phase here. But if you measure the orientation of the filaments relative to the orientation of the disk, you find, and then fold in this polarization information, the magnetic fields are oriented within 60 degrees of the disk plane, which doesn't sound impressive, except that we know that's unstable, right? If you have a rotating disk, presumably the magnetic fields are rotating with the disk, and you have clumps of gas that might be elevated along the magnetic field by radiation pressure or who knows what, right? As a cloud sort of moves along the magnetic field, it's leaving a region of high angular momentum and is drifting into a region of low angular momentum, but it's stuck to that magnetic field. And so as a result, you get centrifugal launching of clouds. So this was first presented by Blanford and Payne in 79. This was as regards to what might be powering outflows within the broadline region. Emmering et al. In 1992, this is what this figure is from to the lower right. And Nelson and Schlossen pointed out that you could actually be powering molecular outflows from this kind of mechanism. So broadly speaking, semi-quantitatively, we're starting to probe a region where there's evidence for a disk instability, a hydromagnetic disk instability that could launch a molecular outflow. And 1068 is known on larger scales to have a fairly powerful molecular outflow. And we think we might be seeing the origin of that within the maser disk. And that's where I'll conclude. I'll stop there. That's where we are with this study. We have, in fact, I'm late to get my SCED file in. We have follow-up observations that are supposed to happen in the spring. So we'll see where this goes.
Thank you, Jack.
Hopefully
Okay.
I'm in time here. I apologize if I went long.
Oh, no. Well, I'm pretty flexible on this. We like
Okay, I went long, I can see. Sorry about that.
Yeah. Oh, anyway, so we opened it up for questions, and we have our first question. And the question is, where are the 1665 and 1667 OH megamaser observed?
Right. So back when I was a kid, when I was a graduate student, we looked for OH absorption in those main lines in 1068. And we were shocked to detect an emission. So there's a paper, 1996, I want to say, where we showed, it was with the VLA, we showed the VLA spectrum. And the beam at those frequencies is roughly an arc second. So we could only say, yeah, these OH emission lines are sort of in the right region. Having said that, I do have, sitting on disk, follow-up observations with the HSA of those lines. And I'm working on those right now. I can only say at this point that there is something interesting there, but I'm uncomfortable sharing beyond that until I really convince myself I believe what I'm seeing.
Okay, another comment question. Wonderful work, thanks. Does the new analysis still require that the disk mass be substantial compared to the supermassive black hole mass?
It's a good question, and so this is in our 2023 paper. That how do I put this? The interpretation was based on a very naive interpretation of the PV diagram. Just you draw a line, you make a PV diagram, and you assume that the where you see a fall off in the rotation curve, those masers are really exactly located on the line of nodes, which is a reasonable starting point. So if you make that assumption, yeah, it looks like the rotation curve falls more slowly. Maybe you've got a self-gravitating disk. However, when you have spiral arms, you don't necessarily expect the maser spots to exactly trace, spots exactly along the kinematic line of nodes. And there's even more complexity, even if they weren't spiral arms, because masers so incompletely sample the gas and velocities, you might be missing the true maximum velocity. There just isn't a maser spot there for whatever reason. And that can kind of fool you into thinking that you're seeing a flatter rotation curve than there really is. So we made some models in the 2023 paper. And I don't want to go much farther down that path because they're all obsolete now. When we made those models, we didn't have any constraint on the kinematic center. And so what we did was we should assume that it's the flattest possible disk, right? Minimize the scale height of the disk to reproduce the observations. But now we're seeing evidence for outflow, magnetically driven outflow. Sorry, I'm kind of talking past myself here. Stepping back, the model that we got requiring a flat disk required the disk to be kind of not quite edge on, but tilted a little bit. But now that we're seeing near systemic masers right against the central compact continuum source, it's almost certainly edge on, and any deviations probably owed to outflow. So now the model's way more complicated. We can't apply a simple 4258 model of just a flat rotating disk. We have to think a little bit about how to accommodate outflow motions along magnetic field lines. And I would love a really smart graduate student to take on that project.
Okay. Just to follow up, I'm going to jump into a
Yeah.
question of my own, and there's just big picture, like the mass of the black hole versus the mass of the disk versus the mass of the outflow, or what do you know the rough numbers on?
Yeah, so I'm a little bit embarrassed. I don't have the outflow numbers off the top of my head. I think you're sort of talking about a solar mass per year or something in that ballpark, but
Okay.
I'm talking into my head. I hadn't thought about it in a while. The mass of the black hole is around 17 million solar masses. So once you correct our original models back to an edge-on configuration. The disk mass, we calculated a slightly different way. We said, look, we can look at deviations from the model, from the simple rotation model, to get an estimate of what we think the turbulent velocity is. Just, basically the scatter among the maser spot velocities, the residuals relative to the rotation model. And from that, we were able to deduce something about the disk mass. I'm kind of embarrassed. I'm trying to remember how I did this. Oh, no, it was simpler than that. The fact that you have spiral arms implies something about the Tumri Q parameter. That's what it was.
Okay.
And from there, you can get at something resembling disk mass, which is much, much, much lower than the mass of the black hole.
Okay, so it's a small fraction. Okay.
Yeah. So I apologize. My memory faded there for a second.
Okay, thank you. Another question. If I saw correctly, it appears as there's a gap of the systemic masers where the compact continuum source lies, presumably the supermassive black hole. If I saw this correctly, how wide is this gap in units of parsecs, and can you speculate on the reason?
Let me share the slide. I'm not sure exactly what's meant here. Let me go back to that slide. So we just want to go back to, say, this slide, I believe, right? This slide on the left. Wow, this is a really crowded plot. There might be a little gap here, right near the continuum source. I'm guessing that's what the question regards.
I think so.
Yeah. I don't know. I don't know the answer to that. I as far as getting down to that level of detail, there might be some maser spots in there, and I've just plotted it very badly in a way that's hard to see. Maybe there's a real gap there. But one could imagine, again, you could imagine that you might be looking at spiral arms that are kind of nested, that you're enhancing one part of an inner spiral arm, then you have an outer spiral arm. They'll all appear near systemic, just based on the way the velocities project. That's crass speculation. I really don't know what the deal is with that gap.
That's fair.
Yeah.
Okay. Any additional questions? We hit the ones that were in the Q&A box. Now, going once, going twice. Okay. Well, thank you very much again, Jack, for your presentation today. I love seeing
Thanks for inviting me.
high resolution data as a radio astronomer, and the AGN is quite impressive, the results you're getting with polarization of the magnetic fields. So thank you, everybody. Our next community Zoom will be in a couple of weeks, and let's see here. It's on Technosignature, Caleb Painter from Harvard. So the 12th of February, right before Valentine's Day. So thanks again, Jack. And we'll sign off now. Bye, everybody.